Let's kick things off then. So first, welcome everyone. It's such a delight to welcome you to the first ever ngEHT science meeting, Science at the Horizon. So my name is Michael Johnson. I'm the ngEHT project scientist, and I'm at the Center for Astrophysics. And in this first session, I just wanted to give you a quick orientation to what to expect this week, what our goals are, and how you can make the most of it. So before we get into details, I just want to briefly summarize, who are we, who's gathered here. So it turns out we have over 460 participants gathered from all over the globe. And it's really one ray of hope in the midst of a very difficult year that I think this is the kind of meeting that never could have happened a year ago. So it's really special that we're able to come together in this way. So throughout the week, we're going to have actually 86 different presentations on science topics across the full breadth of the project. In addition to that, we're going to have 8 discussion sections, which are just dedicated to ideas that you have that have been prompted by the previous sessions. And we have an entire day, the 5th day, which will be group brainstorming in pursuit of developing the full ngEHT science case. So something that I'm particularly excited about in this meeting is that we actually have 43 undergraduate participants. We have 83 graduate students in the meeting, and we have 67 postdocs. So it's a really vibrant community of young researchers, and we're really counting on you to bring fresh ideas and to pick up some of the new ideas that are prompted throughout this week and turn them into new projects. Now, the scientific organization of the meeting was created by a very involved scientific organizing committee. So I really want to thank them for their time and efforts. They put a lot of work into trying to make this meeting a success for you. So that SOC consists of Chung-Pei Ma, Charles Gammy, Avery Broderick, Whaley Penn, Daryl Haggart, Anton Zensis, Alessandra Bonanno, Vitor Cardoso, Shep Doeleman, Ramesh Narayan, Andy Strominger, myself, David Hughes, and Jeff Bauer. So we're really hoping that this format that we've converged on is a way that everyone can get involved. In addition to that, we've had a local organizing committee that's really been working overtime to try to make this meeting seamless, despite the difficulties of a fully virtual meeting. So our local organizing committee consists of Britt Jader, Paul Tita, Nick Conroy, Alex Raymond, Daniel Palumbo, Mina Himwich, Tiffany Nichols, and Lindy Blackburn. So these LOC members are here to answer your questions throughout the week. Certainly if you have technical difficulties, but also if you just have questions about how to get involved or how to engage. So they're available on Zoom and on Slack. Now, as I said, we really want this meeting to be highly interactive. So if you have questions during a presentation, we encourage you to use the raise hand button in Zoom and then wait on the moderator to call on you to unmute to ask the speaker questions. So during presentations, questions will be at the end, but during discussion sections, we expect the conversation to be fluid. So please don't be shy about participating directly. If you prefer, you can also post questions to the Zoom chat. And something that we take very seriously is our meeting code of conduct. So as I said, we have people from all different career stages at this meeting, all different fields and across the globe. So we really are going to work hard to enforce a collegial environment, and we're all joined with mutual respect for each other's academic contributions. Now, the LOC has also created a Slack channel, ngEHT 2021. And so you can join this workspace using a link that was included in your registration email. So this Slack workspace, we're hoping will allow us to continue conversations that come up during presentations and discussions, or to even continue them after the meeting concludes. So any conversations that you're having, if you want to ping someone at the meeting or pick up something from a previous talk, please do that on Slack so that the Zoom chat and Zoom discussion is really only focused on the current presentation. Now, during a talk, you can view the live transcript, closed captioning. So some instructions on this are given on this slide, which I'll post to the meeting website right after it. And you can also disable these. They can be distracting. All the talks and recordings will be posted online. I know these time zones are difficult for many of our participants, so hopefully this is a way to see all the material after the fact. So speakers, please do upload your talks to Dropbox. And in addition to that, we'll be creating a conference photo based on your own submissions. So please upload a headshot so that we can include you in that conference photo. So I just want to give you a brief run through of our schedule, just what to expect, especially today. So we're going to start off, and after my talk, Shep Doeleman will give an introduction to the next generation ngEHT project. And after that, Roger Blandford will give a science talk, giving us some context for the ngEHT, especially historical context. We'll then have a short break, followed by a session on ngEHT concept progressions and pathways. So Garrett Fitzpatrick will give us an overview of the systems engineering. Alex Raymond will talk about the ngEHT reference design. And Lindy Blackburn will talk about the ngEHT data landscape. And following those, Charles Gammy will then lead this moderated summary and discussion. So it'll be 30 minutes where we can really discuss in detail any questions that come up during these morning sessions that we don't have time to answer in the sessions themselves. Now, our afternoon session will start with Mark Reed, who's going to give us a talk on M87 Sagittarius star and micro-arcsecond astrometry. And then we'll hear 2 additional talks by Elliot Broderick on probing accretion physics with the ngEHT, and from Alberto Sassana on gravitational wave observations and synergies with the next generation of gravitational wave observatories. And following that, we'll then have another moderated summary and discussion led by Ramesh Narayan. So please send Ramesh and Charles a note ahead of time if there are specific topics that you think are important to cover. And please do be prepared to show up and participate directly. Today we'll conclude with a poster session. So that's going to start with a lightning round where each of the posters will give just a 1-minute summary of what their topic is. And then we'll go to breakout rooms, 1 per poster, so that you can browse around and see the different topics. So this is intended to be both academic and social, and please don't be shy about showing up. Did you have a question, Shep?
No.
Okay. Now, one thing that's a little different is that on Tuesday through Thursday, we'll have a set of parallel sessions. So these are breakout rooms from the same primary Zoom link. And these are going to be 3 parallel sessions on different science themes related to ngEHT, each with 5 or 6 talks, contributed talks. So I encourage you to make sure that your Zoom installation is up to date so that this process of going to the breakout sessions is seamless. And we don't want you to miss out on any of this exciting science debugging technical issues in real time. Now, on day 5, as I said, this is going to be an entire day where we work together to brainstorm the primary ngEHT science goals and observing requirements. So we're going to start out with a session in small teams, about 5 people per team, and these are going to be organized by topical group, and we'll have a sign-up sheet for that later this week. The second session will be organized in larger science themes. So this will be 1 for GR, 1 for fundamental physics, 1 for jets, et cetera. And these will try to assimilate the goals determined by the smaller teams and come up with a group consensus. And then in the afternoon, each of these themes will give a short presentation of their findings and their conclusions. And this is really the start of formal science working groups within the ngEHT. In addition to that, and just the meeting activities happening, we'll have a few short surveys throughout the week that we're hoping will help track progress and organize our priorities. So today's survey is especially simple. We want to know, why are you here and what are you excited about? And we especially want to know how this might change throughout the week as we hear these new presentations. So there's a link to this forum, and that'll also be copied in the Zoom chat. Please fill it out. I think it'll take less than a minute. So fundamentally, this week is about bringing a new scientific community together. We have experts from astrophysical theory, simulation, instrumentation, general relativity, mathematics, statistics, computer vision, and more. And we're joined by common fascination with the mysteries of black holes. Together, we will define the core ngEHT science objectives, and we'll explore what's required to achieve them. Your ideas will shape the next generation of black hole imaging. So thank you for your participation, and I'm looking forward to a really exciting week. With that, I'll hand it off to Shep.
Okay, thank you very much, Michael. I'll get my presentation ready. Okay, can everyone see that?
Yep.
Okay, thanks. So first, I just want to thank Michael and the entire SOC and the LOC, specifically Michael and Avery Broderick, who were the chairs of the SOC, who architected much of this entire weeks of activities. So hats off to them, and looking forward to a really stimulating week. It's a pleasure to describe the Next Generation EHT Telescope project to you. I think it's fair to say that the EHT was kind of a love affair of all of us, and it resulted in some astounding findings. And we didn't think that there would be another project quite like it. And I'm really optimistic and happy to report that the EHT in its next generation form can be that same kind of transformative leap. Instead of making still images of black holes, we are looking to make real-time movies of black holes with a very enhanced instrument. And that's going to lead to a lot of very, very interesting science. And I want to start off right away by recapping a little bit of where we have come with the EHT and to motivate where we're going with the ngEHT. So the M87 result is pretty well known by now. In the upper left, you see this 10,000 light year dimension image with a jet coming towards us and a counterjet going almost directly away from us. So the jet coming towards us, you see, of course, because it's Doppler boosted, and you see both of them impacting the intergalactic medium on either side. And zooming in by a factor of 10,000, first with the VLBA at 43 gigahertz, and then the GMV at 86 gigahertz, you wind up seeing a self-similar jet with an unresolved core. And that's where the black hole lies, of course. And when you zoom in by a factor of 1,000,000 using the EHT, you finally see this long-sought feature of light bending around a supermassive black hole with dimensions predicted by Einstein's field equations. And if that didn't make you, full of wonder, then hopefully the dimensions of this brought home will. The entire solar system and Voyager 1, which is the most distant person-made object from the Earth, fits snugly inside this entire monster black hole. So the pandemic makes us feel isolated, but this makes us even more so. Now, this is all underpinned first by science. So over 100 years ago, Max von Laue asked the question, what would this black hole look like? What was the impact parameter of a black hole? And he realized that the event horizon, shown here, 2gm over c squared, was the inherent cause of this impact parameter, the inherent cause of the shadow feature. But it was the light photon radius, the light photon orbit, that really defined what it was. And this is the orbit at which light circularizes around the black hole. And when he fired geodesics back from a distant screen, the ones that just were tangent to that photon orbit were the ones that were ultimately captured. They marked the boundary of the captured photons versus the non-captured photons. And the size of this shadow, he determined, was the square root of 27 times the Schwarzschild radius across. There's like a fundamental linkage with the space-time of general relativity around a black hole. And the shadow size and shape encodes, of course, all of GR and the black hole spin. 2 decades of GR MHD, general relativistic magnetohydrodynamic simulations, showed us what to expect. And they showed us that we needed to see down to the event horizon with 1 millimeter wavelength radiation. That was the wavelength at which the accretion flow becomes optically thin, and that lays bare the accretion flow lensed by the space-time around the black hole. This is a wonderful simulation by C.K. Chan and the University of Arizona group. Now, the other component that allowed us to make these EHT measurements was, of course, a revolution in the VLBI instrumentation. The very long baseline interferometric technique allows us to make an Earth-size dish by aggregating dishes around the globe, bring data back together, correlating them, making a dish the size of the Earth. And we managed to do this by keeping pace with Moore's law. This was absolutely essential. So the bandwidth of our systems were tied to commercial off-the-shelf technology, which dramatically reduced our time to science and allowed us to increase the data throughput of our systems by 2 orders of magnitude during the course of this project. Without this, we would not have been able to make the measurements that we did. Now, the first full observations took place in April 2017, of course. We had 8 stations, and they're shown here. We had the SMT in Arizona, the LMT in Mexico, the SMA JCMT in Hawaii, the OPEX and ALMA dishes in Chile, South Pole at the South Pole Telescope, and the IRAM 30 meter in Spain. And all of these telescopes working together gave us the inset Fourier spatial frequencies you see here. And we had enough of these Fourier spatial frequencies that we could invert it to make an image of the black hole. And the weather we got was really extraordinary. When you have only 8 dishes, you really need the weather to be good at all of your sites. And one of the differences that we'll see with the ngEHT is that we'll have so many dishes that we can lose a few here and there and still make remarkable scientific images. Now, this also, in addition to all the ingredients that I've described to you, we also required novel analysis techniques. We needed to reinvent some of the imaging algorithms that we use for VLBI. And we used regularized maximum likelihood methods predominantly, but also the clean technique, in which we fit for the data, but also used regularizers to help steer the process, making sure that the images were smooth, that we understood the gradients across the images themselves. And all the papers on the left here show the sequence of improvements of this technique. What I'm showing here is all the different stages in a kind of an average kind of imaging run, in which you see the data being fit, the regularizer steering things. You see an annealing stage there where it comes out, comes back in. And with these new techniques, we were able to get unparalleled image fidelity in this new regime. And these were tailored for the Event Horizon Telescope case. Now, let's turn right now to one of the primary results that will motivate the ngEHT. We predicted that we would see this ring, but how do we measure the mass from this ring? Well, it turns out that on the left here, you see the a GR-MHD simulation, and you can clearly see the ring of light that marks the photon orbit, and that's shown here in the white dashed line. Now, when you make the actual image, the black here shows the brightest part of that ring, and it's biased outward. And that's essentially because you have a lot of emission shown here outside of that ring. And the question then becomes, how do we relate the observed ring with the actual photon orbit? Because it's only by understanding the photon orbit that we can measure the mass. The relevant equations are just shown here at the top. We measure the angular shadow diameter, and we want to relate that to the measurement of mass over distance. And we write that as this equation with theta sub g being the angular gravitational radius. But we want to understand what this bias is. So we make the assumption that the angular shadow diameter that we measure is proportional to that gravitational radius. We want to find out what that constant proportionality is. And to do this, we used a novel GR-MHD calibration technique in which we took hundreds of simulations. We created synthetic data sets from those simulations. We sent those to the same imaging pipeline that we used for our normal VLBI data, and we compared the known photon orbit radius with that derived from the images. And in this way, we were able to empirically fit what this alpha, what this constant proportionality was. And it turns out to be about a 10% bias outward from the true photon orbit. But in doing so, despite the fact that, as you see here on the right, we got excellent results across all days with all the different imaging algorithms. Despite that, we incur in this process an unavoidable 10% uncertainty. Because we are imaging this very tufty, large, wide ring, we are limited in the ability to test GR to a validity of about 10%. Now, knowing what the distance to the black hole is, we were able to invert this mass over distance measurement to get a mass of 6.5 billion solar masses. Now, this is quite extraordinary. We're laying a ruler across space-time, measuring the mass of this black hole for the first time with completely independent means. So at the end of the day, what have we found so far with the Event Horizon Telescope? Well, the black hole shadow we feel is clearly detected. The image morphology that we found is completely consistent with all expectations from these relativistic simulations that we run. The asymmetry that you see, the fact that the image is brighter on the bottom than on the top, is due predominantly to lensing and the Doppler boosting. If the spin is aligned with the jet axis, and we think that it has to be, then the black hole spin is pointing along the counterjet. To see this, take your thumb, point it into the page slightly down to the left in the direction of the counterjet. Your fingers curl up and around, and they show the direction of the relativistic flow around the black hole, and so it's brighter at the bottom in the position of your fingers. Now, GR is verified at the 17% level. And we say 17% because when we look at other determinations of the mass of M87 from stellar dispersion, they match the mass that we have derived at this level. But again, the GR-MHD calibration that I described earlier sets a limit of 10%. There's a limit of 10% that we can't pierce using the kind of techniques that we have used so far. Now, I want to motivate the ngEHT by asking three basic questions. And the first is, can we test GR to better precision with the shadow? And I think that we can. And this comes from some wonderful work by Michael Johnson, Alex Luksaska, and others, which show that the image that we've observed so far consists of multiple rings. The first ring is what we call the n=0 ring. This is light that's gently bent around the black hole, which gives us that broad, wide ring. But if we can look at photons that make a full U-turn around the black hole, these photons give us a much more narrow feature that is tightly coupled to the photon orbit. Measuring this would reduce the need for using this GR-MHD calibration technique to tie what we see to the true photon orbit. So zooming in, you'll see what I mean here. The entire ring here consists of this n=0 emission, which is very broad, but the n=1 emission is tightly coupled, very closely linked to the true photon orbit, shown here in this bright, bright ring here. Now, the Fourier decomposition of that n=1 ring, because it's so narrow, has deep nulls that you see here in the black that extend for many gigalambda in baseline length. And shown here in green is the ngEHT sampling of those baseline lengths. What this shows you is that for the n=1 ring, you can sample many or multiple of these nulls and determine its exact diameter and geometry. This will allow us to get through this 10% noise floor that we incur when we use the GR-MHD calibration. What's really encouraging is that Avery and colleagues have started to use a hybrid approach to this, in which they use the fact that we expect the ring to exist because we know that it does, and we fit that ring, and then we image the residual large-scale structure separately. In the upper part of this diagram, you see multiple GR-MHD simulations. In the bottom here, you see a hybrid fit where we fit the ring first, then subsequently image the large-scale structure. And the posteriors at the bottom here are showing that Avery and his team are reliably extracting this ring-like feature to sub-micro arc-second precision. So using the known ring structure, we can super resolve using the next generation instrument if we have high signal-to-noise ratio data. So the first thing we need to do is increase our sensitivity. The second question to ask is, where's the M87 jet? We see this amazing 10,000 light year across jet, and we see this equally amazing black hole image, but where is the connection? Where is the jet feature that we would expect from these simulations? GR-MHD simulations show that this jet is launched very close to the black hole itself, but this region here is extremely low surface brightness, and the dynamic range of our baseline lengths with the current EHT is insufficient to reconstruct that jet launching region. So we need much higher dynamic range in order to recover this jet launching region. And the third question to ask is, can we exploit time variability? So a GRMHD simulation that you see here on the left shows that over short periods of time, Sagittarius star, which is the 4.5 million solar mass black hole in the center of the Milky Way, should change its appearance from moment to moment. In fact, GM over C cubed, which is the light crossing time for this black hole, is only 20 seconds. And the period of matter orbiting around Sagittarius A star is 30 minutes. So within one night of observing, we need to make many, many images and stitch them together to make movies. So we require movies with innermost stable circular orbit period precision, which is much better than we can do right now. This is one of the reasons why we have been slow in coming with the Sagittarius star results from the ngEHT. We have to wrestle with this time variability issue. So this brings us to the next generation instrument with that motivation. You'll hear a number of talks about this in the coming session, but we have asked the question, where can we build out the array to increase our imaging fidelity and our movie making capacity? In blue, you see all the sites that we have currently in the ngEHT, and red, all the high altitude sites where we have relatively good weather and we can increase the Fourier spacings that we can measure. This is work being led by Alex Raymond and a team here at the Smithsonian Astrophysical Observatory. Now, the concept behind the ngEHT, the motivating idea, is that we no longer need large dishes to fill out this Earth-sized virtual telescope. This is a plot that shows the sensitivity of a baseline versus the diameter of the dish. And you can see that for relatively small dishes, let's say 6-meter dishes, we can meet the design spec of 50 millijanskis of sensitivity when we pair that small dish with a large anchor site. So whether it's ALMA, whether it's the Large Millimeter Telescope in Mexico, or the phased NOEMA array in France, if we can pair a small dish with those large anchor sites, then we can achieve the required sensitivity to dramatically increase the UV spacings of the next generation instrument. So with this in mind, we've embarked upon a design process for the next generation ngEHT instrument. The phase 1 that we're in right now will be a design phase that will conclude in 2024, and phase 2 will be a build out and commissioning, which will lead us to a completed array by 2030. The concept is that we'll have new stations, about 10 small apertures at optimized locations. We're going to increase the bandwidth by a factor of 4, increasing the sensitivity of the entire array by a factor of 2. We'll observe at a new band, 0.87 millimeters, which will increase our angular resolution by 50% immediately. The data volumes will reach 10 to 100 petabytes. So it's going to be a very, very large data project. And we'll achieve these data rates with high-speed data capture and transport, again, leveraging commercial off-the-shelf technologies. Now, interestingly, the data processing is going to be a challenge for us. We'll need to increase by a factor of at least 16 the computational capacity of our correlators and our image processing. And to do this, we plan on shifting to the cloud, where we can nimbly assemble very, very large virtual machines to process all of this data. And underlying all of this will be optimization of algorithms. We'll need new multi-frequency synthesis techniques, dynamical imaging to make movies in order to understand this massive influx of data. The estimated cost on the right here is about 140 million for construction, and the operation will be about 10% of the capital cost, or 13 million per year. This entire concept was sent into the Astro 2020 review process, and we eagerly await the results and the findings from that. Now, what can we do with this new array? And this is really what is going to consume, all of our attention for the coming week. But if you have these two wave bands, 0.87 millimeters and 1.3 millimeters, and you sample with 10 to 13 new sites around the globe, you get the Fourier coverage you see here on the left. And in black and gray, you see what we can do this coming year at 230 and 345. And in blue, you see the remarkable enhancement that we get when we add 11 new dishes for 345 gigahertz and 13 new dishes for 230 gigahertz. On the right, you see that same jet simulation that I showed you before. And if we try to image this with synthetic data, this is what the different stages of that minimized, regularized maximum likelihood image is. And you see that the final image is very close to the input model image. We can achieve the dynamic range required to map the energy extraction region from the black hole all the way out to the jet launch region. Now it gets even better than that, because with M87 we can observe every week or so, and on the left you'll see a real-time movie, a GR-MHD real-time movie of the black hole jet system, and on the right a stitched together movie from synoptic measurements made by the next generation EHT. Now you can see on the left detailed helical structures emanating from the black hole itself, and on the right we recover those with very, very high fidelity with the next generation instrument. So when we talk about making movies of black holes, this is what we think is possible. These fidelities, these surface brightness sensitivities, this dynamical information from the M87 black hole, we will see energy extracted in real time from a supermassive black hole. Now for Sagittarius star, it's a little bit more complicated. As we described before, GM over C cubed is 20 seconds. That's the light crossing time of this black hole. So we need to make movies with frames that are about 100 seconds in length. On the left, you'll see a simulation of a GR-MHD movie. In the middle, that movie is just simply blurred, so you can see all the structure that you would hope to get. And on the right is a reconstruction with the with the ngEHT, and the inset shows the instantaneous UV coverage as a function of time. And you can see in the middle, it's very clear the direction of the rotation and even the speed of the rotation. And on the right, with the reconstruction using current algorithms, we can closely follow that changing morphology as a function of time. So this is just what we can do with current algorithms. And we have many, many years in front of us to refine these algorithms to determine what the rotation around the black hole is as a function of radius, and that will let us map the tomography of space-time around the black hole itself. This is going to be an extraordinarily rich vein of study for horizon scale flares, magnetic field dynamics, and also precision black hole orbits. Now, the last part of this is to go back to this idea of fitting the n=1 ring. And with the ngEHT data, it's so rich, it's so high signal to noise ratio that we can ask the question, could we detect M87 if it was farther away from us than it is now? And Avery and his team have run simulations in which they put M87 at 50 megaparsecs from the Earth, which is 3 times farther away. And the top right, you see the truth image showing the large-scale jet and the ring around the black hole, and the reconstruction that they get in the bottom using these hybrid techniques in which they fit for the photon orbit, and then they image the remainder of the large-scale structure, shows that we have great promise in pulling out these structures close to the black hole for objects that are much farther away. And the reason that's important is that the accessible volume in which we can search for black holes and image black holes increases by the cube of this angular resolution. So with these techniques, if we can increase our angular resolution by a factor of 3 to 10, we increase the volume by 30 to 1,000, with potential access to many more horizon targets. So the design phase right now, I'm delighted to report, is funded by a $13 million mid-scale research infrastructure award from the National Science Foundation. It funds the Smithsonian, UMass, MIT Haystack, and Caltech to carry out this design. And we are accreting new partners all the time from across the Event Horizon Telescope collaboration and beyond. There are 2 main activities. The first is to enhance the performance of the ngEHT and to prototype key systems. So we're developing a dual band receiver. The UMass is leading that. We are exploring the LMT daytime operations to make that a firm anchor station for the next generation EHT. OVRO, with its 10-meter dishes, are coming online through the work at Caltech. And even at Haystack, we're exploring use of the 37-meter at 1.3 millimeter wavelength observations. Most importantly, we're designing and planning the ngEHT. We are studying and designing small dishes to be put at new geographic locations. We're designing next generation backends. We're architecting new data pipelines and designing and testing all the new analysis algorithms with optimized layout through simulations. The idea is that we want to come with a full proposal for construction, again, through the MSRI program, with international collaboration and backing by 2024. A basic, I'm not going to go into great detail here, but a basic work breakdown and timeline falls along 4 main verticals. It's all underpinned by the science at the left, and there we are aiming in the next few years to determine all the science requirements, write all the science white papers. We're studying analysis and data pipelining with a goal of doing end-to-end science simulations, but also determining the data processing pipeline specifications. On the technical side, we want to bring to preliminary design and, to the extent possible, critical design of major subsystems, including antenna fabrication. And it all comes together on the right with systems and architecture, where we want to derive a full operations concept, an ngEHT station design, and an implementation plan, which we can take to the National Science Foundation and to other funding agencies. We coordinate all this with monthly international ngEHT meetings so that we can coordinate with all of the collaborators globally. Now, this particular meeting deals with the left-hand side here, and I'm extremely excited to see all the different kinds of science that will be discussed. And as Michael said at the very end, we'd like to bring this all together with an understanding of how we will determine the science requirements for the instrument. And the general timeline is shown here at the bottom. Now, I want to point out there are a couple of clear differences between the ngEHT and the EHT. For the ngEHT, we know that the shadow exists. It's a huge advantage to determining the design of an array like this. And strong GR signatures will be visible and observable. This is something that we did not have for the EHT. We were flying blind in a sense, but now we understand what we can design for. The EHT design was much simpler. We had fixed geographic sites. We were not building any new dishes. So it was an easy goal to maximize the bandwidth, maximize the sensitivity with what we had to make the best imaging that we could. For the ngEHT, it will be a complex optimization space. We have new dishes, and the number of the dishes required, the size of the dishes will be the topic of a detailed optimization process over the coming years. And the science that we do will be a key part of that. As Michael said, the ideas are going to drive the instrument at this point. The ngEHT project is also larger in scope. This is a $200 million project with 7 years of operation built into it, a factor of between 5 and 10 more expensive, more costly than the EHT was. So we'll have to engage in best practices for system engineering and project management in order to bring this to a successful conclusion at the end of the decade. And the operational model is going to be different. The EHT observed in campaigns, but the ngEHT will have many more observing possibilities, observing throughout the year, nimbly sidestepping bad weather, only lighting up when we have very, very good weather. And the EHT used expert observing. People go out every year to the EHT sites, but the ngEHT is going to require near fully remote operation to make this a success. So in summary, I want to leave you with a couple of points here. The first is that the international work on the ngEHT design is underway. We've already kicked this off. Of course, it's happening during the pandemic, so there's been some slowdowns, but we are working with international colleagues. And this meeting is absolutely a critical part of that. The ngEHT is a visionary project. We're going to produce the first black hole movies. As I like to say, we're looking for executive producers, so count yourself among them. This will be a project with every bit of the same impact, I think, than the EHT did. So if you're looking for a project that you would like to contribute to over the coming decade that will have very strong impact across the sciences, uh, I, I think this is the one. This workshop that we are engaged in right now is a vital part of this process. We're going to be developing consensus science drivers collectively. The ngEHT architecture is at a formative stage, so that what we do here will drive the design. And we're going to form an ongoing science development organization, which we'll discuss during the last day. We're going to describe for you how you can remain involved, how you can remain a part of this design. And I really feel it's important to say that we're committed to an inclusive program with leadership development and opportunities for early career researchers. Within the EHT, early career researchers played a very important part in all aspects of the project, and we want to continue that with the ngEHT, creating strong opportunities for people to take leadership roles. So the target for 2024 is for the final design, and we want to come with an international proposal for construction and completion by 2030. We do anticipate that 50% of our construction costs are going to come from non-US contributors. So this truly is an international effort similar to the EHT. And the following presentations on the ngEHT are going to give you all the rest of the details on the systems engineering, the reference array, and the data processing. And I'm just going to leave you with this final quote from the Astro 2020 ngEHT white paper. In 2010, we said we would come with first images, and we made it with just a couple of months to spare. And now our prediction is that we're going to outline a process. We're going to design a new global array that will make the first real-time movies of supermassive black holes and their emanating jets. It's a remarkable prediction. It's a remarkable project, and welcome to the science definition team. Thank you very much.
Thank you, Shep. So one of the great difficulties we have on these Zoom meetings is applause is difficult to provide. So let me be representative. We do have some time for a handful of questions. I would request that people make use of the raised hand feature in Zoom. I would also remind people that there's a discussion session at the end of the morning sessions when questions can be asked on this and the rest of the talks in this morning. And we have the Slack message group where we can include questions, or people can submit questions both on and off topic and receive asynchronous responses. So with that, I see Haupt has raised his hand. Please, Haupt.
Hi. Yeah, Shep, you know this question. I've asked it before. Can you elaborate on what you see there as the role of ALMA for this array of optimized small dishes?
Yeah, it's a great question, Haupt. As I pointed out, it's the anchor stations that allow the small dish concept to flower, and the ability to use 6 or 8 meter dishes all around the globe to fill in all the UV spacings is critical for the ngEHT concept. That being said, there are a number of other large apertures that can be used as anchor sites. So the LMT, most notably, being at the geographic center of the entire array, will play a large role. And as you saw in that in the sensitivity calculation plot that I showed, the LMT and NOEMA, when it's phased, will also be able to serve as anchor sites. So between all 3 of those, we think there's this ample opportunities to have those anchor sites build out this array. So we're not dependent on ALMA, but its participation is going to amplify the ngEHT.
Understood.
So we have a second question from Sarah Birch-Spolar. Sorry if I missed this, but with such amazing capability, are there plans for open observing or imaging of other targets than the ones for which the movies are planned?
Yeah, it's another great question. So certainly there's abundant jet physics to be done, even for sources for which we can't resolve the event horizon. And there are some new results that will be coming out from the EHT that emphasize that and demonstrate that. So there's certainly a very broad science case to be pursued with the ngEHT in addition to the event horizon scale sources. And looking at the large scale jets at unparalleled resolution is going to be very, very interesting.
I think I saw Jim Gates, you had your hand raised. I'll give you the final question. Juan, we can return to your question during the discussion.
Thank you very much. And thanks for that great presentation, Shep. My question is actually a long range blue sky question. If I move out to 2030, where you have this larger volume of being able to detect black holes, can I think about using them as exploratory tools to actually think, to consider questions around dark matter?
Oh, that's interesting. There are applications for this. Certainly, the M87 has been used to constrain some of the warmer, hot, dark matter like axions. I'd have to think about whether or not many more sources would help that. It is certainly something that we should discuss during this week. I think there is a section on fundamental black hole physics that will deal with that. But that's a very, very good question.
Thank you.
Let me echo that, Jim, that there's one of the purposes of this meeting is for us to think of all the things that we haven't thought of before about what can be done. Okay, so with that, thank you, Shep. Now it's time to move on to our next talk. So first, science talk. Let me add my voice of welcome to everybody here and say we're going to begin the science portion with an astrophysicist who's synonymous with black holes. Nearly immediately after Penrose suggested that rotational energy of spinning black holes could be tapped, Roger Blandford developed and presented the first models that practically did so. The Blandford NIAC mechanism, one of the leading models for the launching of astrophysical jets that propagate the influence of black holes to even intergalactic distances. So it seems that Roger, along with black holes and magnetic fields, is a critical component for jet launching. That is, all of the mechanisms that we talk about testing with instruments like the ngEHT bear his name, things like Blandford NIAC or Blandford Payne. And therefore, it is fitting that Roger would lead off with one of these plenary science talks. Roger, are you there?
I'm here, but whether you can hear me I think is a question.
Oh, brilliant. I can hear you. So then, without further ado, why don't you take it away, Roger?
Okay. I think I should probably try and share my screen. Is that okay?
Absolutely.
And so bear with me. So I think I'm doing this one. I'm going to share that. And then I think I want to go to, excuse me. I show, wait a minute, that one. Interview or something like that.
Looks good.
Okay, we've just seen the whole talk, so that's good. Okay, can you still hear me and see the screen? Is that okay?
Yes.
Okay, all right. Well, firstly, thank you very much, Avery, Michael, Shep, and everyone else for inviting me to give this talk. I'm very honored to be asked to be here. And I was asked to sort of kick it off. And I actually prepared some slides, which were sort of perhaps a much worse version of what Shep just said. So, and I've been removing those while he was talking and swapping in some other ones. And so it's going to be a little bit amateurish, the presentation, but I hope that I will stimulate some discussion of some of the topics that are going to come up in this week-long meeting, whose exciting synopsis I have just been reading. So I've only really got caught up with the full scope and intent of this meeting, and so apologizes to some duplication. And most of what I will say will be covered in much more detail by subsequent talks, and I'm not trying to do that. But I would like to try and put a few quixotic or non-standard ideas on the table, not because I'm completely convinced that they're all right and wrong, all right and everyone else is wrong or anything like that, but simply because I think there is a need for a broader discussion at this early stage in what I trust will be a long scientific adventure. So in that spirit in mind, I was asked to talk more about the science, and in particular to talk about electromagnetic energy extraction and so on, which I'm very happy to do. And I will, in the end, actually follow that direction a little bit more than I'd intended. So, so my plan is really to try and just give a little bit of quick context, less than I might have done, and then say a little bit about black holes and distant jets and electromagnetic fields. And then I'll talk about just a few thoughts about what I hope is probably the main thrust of this meeting, which is the future, where it's going. And there's big choices that are going to have to be made as you plan a route forward to ngEHT and beyond. So I'll make a few comments about that at the end. Okay, so the EHT observations of M87, for you, it happened a couple of years earlier, but for the rest of us, it happened in April 2019. And there was this spectacular image produced by telescopes all around the world. And this was a larger cultural event than, I think people who were involved in the project were sort of pretty convinced that they were doing something important and lasting. But I think the symbolism is I think, tremendously good. I think it's symbolic in two rather separate ways. One is just that image on the left-hand side says people in different countries are all working together to make something that's bigger than each of them individually. And when you recognize that the people involved are actually astronomers, then it becomes an even more impressive feat to have them all work together and produce constructive interference and so on to produce the image on the right, which was a wonderfully sort of iconic view. Just, I mean, it had its own graphical impact, but it also, I think, underlying it, not very far below the surface, was a genuine scientific story and a scientific detective story, and it sort of combines, physics and engineering and technology and so on, and bringing the latter in to advance the former is great. And the idea of black holes is very much in the popular culture, since it wasn't actually John Wheeler, but he could coined it independently. Someone called Anne Ewing, I think, was the first person to actually use the phrase in this context. But in the 1960s, and it has sort of been very much part of the lexicon of politics and economics and so on. But actually seeing that these things exist, not just as some sort of vehicle for a science fiction movie, but they really are out there. And furthermore, the next level down, that there are, whatever it is that you're looking at in the shadow, it's about the right size and in the right place, and it's black, which is what it's supposed to be. It isn't some sort of pentagram 5 times the size or whatever. It's it's something that we would all take for granted, but I think for many other people, and I've talked to lots of people about this, just seeing that was, stunning. And this is science at work, and it's a time when one needs to affirm that science does work. This is just one rather important example. And of course, this was in the black holes are sort of became quite famous. Then, of course, they were famous before, and they became even more famous for scientific reasons. Of course, there was the LIGO black hole mergers, there's the ongoing story of gamma ray bursts, for which there was long an epoch when the number of published theories significantly exceeded the number of examples, but now no more. We now know there are basically 3 fundamental types of gamma ray burst, and 2 of them involve black holes very seriously, and they make the jets and so on. Here's a cartoon here, and that was, of course, 1708-17 was sort of persuaded most people that that was what was going on, the short gamma ray bursts, and then there's the association, of course, of the jets in the AGN and so on, which we'll see a bit more of, with cosmic rays with energies comparable with that of a well-hit baseball, and PeV neutrinos and so on. And then, as last year, the wonderful, exciting award of the Nobel Prize to Roger Reinhardt and Andrea. And my first reaction was I was completely thrilled that they had been recognized in this way for quite different contributions. And for what it says about black holes and so on. But I have to say, my second reaction when I saw what this graphic was, well, maybe black holes have hair after all. But it's a very exciting time for black holes, and you're going to ride this horse as far as you can. Okay, but there was also, of course, some skepticism when your image first came out. I sent it to my collaborator, Naomi Globus, and her first reaction was to send me this. So it's all a big fake. And then there were cartoons like I think this. So in that spirit, I'm going to change my background on my slides to black and say a little bit about the context of VLBI imaging. And say a little bit about context. And this is not in any sense any historical thing, but I would just like to, somebody who's watched from a safe distance the development of interferometry, I would like to pay a homage to the giants on whose shoulders you all stand, and with your gigantic accomplishment. Going back to closure phase and closure amplitude, all the people who carried equipment through customs all around the world, and all the practical problems that were solved. This is not a historical or a fair or a complete list. They're just some of the people I happened to meet along the way. And but it was an awful lot of scientific development, technical development that went on from the 60s, to today, and on which, Shep and Heine Falke in Europe and many others, Tony Zensus and so on, all those who who you are, and it's been a great journey, and the leap that's been taken by ngEHT with a lot of help from people who work in observatories, who helped install completely new equipment and recording devices and so on. It really has been a large number of people involved, and I think it's a very large international family, and it's important that the whole enterprise, as I know you recognize, continues in that way. So congratulations to all and all that came beforehand. Let's take a little bit of the science context, and I'll focus mostly on M87. There's a lot, I've given whole talks on M87, but let me just make a couple of points here. Of course, it was over 100 years ago that the first jet was sort of identified by Curtis, and then M87, of course, was very seriously studied, and the compact and the dark object in the center, as I think it was somewhat coyly called by Sergeant Young and others, in 1978, I think it was, 5 billion was what they got. And as you know, that mass has gone up and down. Actually, something that's and of course, it's been observed through radio, through gamma ray. Walker et al. Monitoring, I think, for the jet physics was extremely important over a decade or so. the X-ray astronomers and others got in on the act with demonstrating the environmental impact. This is not a historical observation, but it always amuses me that M87 with its 5 billion solar masses presumably wasn't born that way and grew. And if it grew, it was almost certainly brighter than Vega in the past, if you look at it on the sky. So it, it would be a very prominent object. And it's another way of saying that is, and something I'll return to, it's a very underfed, to the point of near starvation black hole, not because of the amount of mass that's flowing to the center of M87, because of its enormous mass. And you all know that, and but I'll just emphasize that point there. Obviously, Sagittarius Star is a big part of your program, and we're all eagerly awaiting and results, of course, more results. I mean, there are plenty, but there are be more, and fully sympathetic with the challenges that the rapid variability causes. And then, of course, you're also, and have already published, for example, in this 279 montage and so on, other jets where you're not going to resolve the black hole anytime soon, or its shadow or anything, but you can tell us a lot more about the story of how jets are paired, how they are formed, how they're collimated, and so on, how they shine. All of those things are directly observable, and as one looks at black jets on different angular scales with the same earthbound array, then of course one builds up a common picture. So that's all great. So here's a bit more about M87. Of course, you don't need to see any of this. You know all of this, but it's seen throughout the electromagnetic spectrum, and gamma rays not actually shown there. And then just the Milky Way galaxy. This is not your image. This is one from obviously from South Africa, but it's a spectacular image, and it shows what a rich and complex region, the center of a galaxy, and even a pathetic one like ours, the nucleus of our galaxy looks like, how complicated it must be, all the physics that's going on. What are these streaks? Are they magnetic field lines? What are they? This is a wonderful observation, of course, and again in the larger context. And I apologize for the top left-hand corner, but I think you're all part of the same family. There are jets everywhere. If I just, obviously you know all of this, but in the previous slide was, of course, the ngEHT image. But if you use, as Jim Condon did, and many others, I think he was the one who gave me this, use it as a means of counting faint radio sources, which you can, then there are basically, I think the arithmetic is roughly about 2 billion. You're now counting down with ngEHT down to about 2 billion radio sources on the sky, half of which are believed to be basically black holes with jets. So, it's not an occasional thing. Jets, of course, happen in the Crab Nebula. They happen in another ALMA image, HL Tau. This is a protostar, for heaven's sake, SS433, seen now in TeV gamma rays, possibly seeing the PeV neutrinos from 0506, and then there was 170817, which everybody said, well, at least there's not a jet there, and you might as well go home, you radio astronomers. You're not going to see anything. But the radio astronomers, as we all know, are very stubborn people, and of course they waited and they observed, and they found, what did they find? They find a jet. So it's the jets are everywhere. It's not a special thing to happen. It's really a very common thing that happens in many, many different physical circumstances, and there's almost certainly not one simple explanation that explains everything, like the gamma ray bursts, which turned out to be 3 quite different physical phenomena as far as we can tell. And the same may well be true for these jets. So cracking the jet production in M87 is not going to be solving the whole jet. There's going to be much more astrophysics to be understood, involving quite different processes, I imagine. So, but having M87 focusing on M87 is a good thing to do. Okay, let me now sort of segue into physics. And I think this is what I was asked to do. And I apologize to Charles and others if I'm not following my instruction. And I'm going to go off, as I say, on some tangents here to put some alternative thoughts on the table, not with strong personal, as I say, I emphasize, not with strong personal conviction, but because I think at this time it is appropriate not to have too much groupthink in the interpretation. Okay, so well, here's firstly the equation at the top was created in something I still, you know, wearing an applied mathematical hat, I still marvel at how it ever happened. And I mean, I've read the story, but it's still a remarkable feat to find the analytic solution to Einstein's field equations that describe a spinning black hole. And originally it was describing some sort of spinning space-time. I think that was pretty clear. But over the next few years, a lot of hard work, some by people on this side, demonstrated that to all intents and purposes, it was the solution for a simple two-parameter family with mass and spin in an asymptotically flat space-time. And there are, of course, many other solutions of relativity, but this is the one that the conservative view is this is the one for astrophysics, and all the other things are wonderful fodder for the febrile imaginations of theoretical physicists, and they have actually turned out to be touchstones for asking and answering a lot of very important questions. But their utility in astrophysics is somewhat questionable, and I'll say that in a moment. But let's just take the Kerr metric we know and love. As I say, it's characterized by mass and spin. And as Roger showed, or as Avery just mentioned and Roger showed, that rotation is in practice extractable. There are various ways of doing it. One way is to throw rocks in the wrong way into the black hole. Another is to use electromagnetic field. And it's the second one that I'll discuss in a little bit more detail coming up. But the black hole essentially has a well-defined kinematic angular velocity, and up to 30% of its mass can be regarded as extractable. And as happens with gravitational energy, you can take out, you're unlikely to get all of that in the same way that automobiles aren't 100% efficient. There's going to be a lot of dissipation, a lot of lost energy, but to expect 30 to 50% of it is not unreasonable to be extractable by, I would say, by electromagnetic fields. So let's just move on. And so let me just say a little bit more about that, because it's going to come up in several of the talks that are coming, and I'm not going to try and get ahead of them. People giving these talks will present their current views, and I hope to be able to hear some of them, and I'm particularly interested in learning what people have been thinking about recently. But as I said, there's probably two views here. One is a sort of pragmatic view, is that it's just the Kerr metric we're looking at. This is in some sense, in a sort of theatrical way, this is the bare stage on which violent cosmic dramas are enacted. It's like watching Beckett or something. And even that, if you take that sort of limited view, then there's that background is ample for a host of well-posed physics problems. And just taking that view, I think is not, there's plenty of work to be done, in the interpretation and theory side of this. And then there's a sort of more exploratory view, which is that, as I say, in the sort of spirit of theoretical physics, there are many elaborations. The first and most immediate one, which was well worked out and has a lot to commend it from the point of view of mathematical physics, is charge. And adding charge to this and getting Kerr-Newman black holes and so on is worth thinking about. My own view is that it's very, very hard to sustain gravitationally significant charge. There's a little charge in the black hole inevitably, but anything that's gravitationally significant, I think, is terribly hard because it discharges so easily. The vacuum's that sort of level is a perfect conductor, and it will discharge essentially immediately. there's the possibility, always has been, of there being new scalar or even different types of fields that emanate from black holes that are somehow also associated with it, has air, if you like, again, no evidence for that, but still worth thinking about. You and combine sort of theoretical work with observation, look for these things. Naked singularities, people have talked about those. I mean, it isn't completely proven, and there are sort of legalistic things, but it looks like most singularities are respectable. But it's worth thinking about, and there have been papers recently about that. Firewalls, the theoretical physicists got very excited about the possibility of there being firewalls and so on. You found no evidence of that, but again, worth thinking about. Strings, there have been papers about that recently. A lot of interest recently in that you might have dark matter, might be low mass axions, and they may congregate around black holes and so on. Again, this is subject to observational investigation, and again, well worth thinking about and limited to detect. And the sort of generic thing is, without anything very specific to say, I think the polarization might be very prescriptive in this regard. Let me move on. And again, I'm looking forward to some discussion of this. I mean, I think I've always understood about the photon ring and thought about the caustics of black holes and so on, but I've never been entirely clear as to why in a model it should be so prominent that you're looking for the emission and absorption along geodesics that will circle the black hole. That's certainly true sort of kinematically, but you've got to ask, is that going to dominate the emission that you actually see? And is it so special? If you can see it, it's wonderful. But I'm looking forward to some bit more discussion where I might ask a few more questions than is there, but at least I think this is, I've been a little bit bemused by why it's such a focus, if you like, of the discussion of the ngEHT observations. Again, I'll make this remark that polarization could be especially diagnostic in the search for new physics, and as Avery in his thesis sort of thought about quite a bit, there's the possibility under some models that the plasma effects are really rather important, and that will rotate the plane of polarization and so on. There's a lot that could be going on there. And if we look at this, I'm going to transition a little bit more to the problem of jets, and this is where I'm going to get into hot water. As I say, there are many models, I think, that should still be considered for the production of jets, even in the context of M87, let alone all these other possibilities. And if you ask about the sort of choices that are out there, the fundamental ones is, are they powered by spin or the disk binding energy? And I'm going to, I've always argued that it's probably these sort of jets at least are powered by spin. Then there's a question of what collimates them. What takes something that will naturally want to expand more quasi-spherically, and what makes it into a very impressively narrow jet? What causes the collimation? Well, magnetic field, I think for most of us is, in fact, on observational grounds is the best bet. But it could be that a lot of it is defined by essentially quasi-stationary torus, and again, I think for the most sensible thing for the magnetic field providing the collimation is that it's associated with the wind emanating from the disk. And then obviously for an astronomer, what's the emission process? What's the emission? I think, again, for many people, and certainly going back to the 80s and so on, the notion that there might be, some boundary layer there, some sheath, and that the emission is coming from particle acceleration and field amplification in that region is, and now has a lot of observational support, and that will be discussed further down, particularly the radio astronaut observations and so on in 1275 and elsewhere. One sees the emission coming from the boundary of the jet, and that's not unreasonable. But I think one thing that needs to be sorted out a bit observationally is how much emission is there coming from the core? Is it essentially low dissipation and an expanding flow with nothing really causing dissipation and essentially visible for that region, or is it ultra relativistic and emitting quite impressively, but being beamed, in most cases, just being beamed away from us? And I think that's settleable, I think, observationally, given the quality of observations that are promised. So let me talk a little bit about M87 and what I call the jet problem, and it's been one that's been around long before the EHT observations. The first is the jet is, and this is going to be a little pejorative here, but this was actually the calculation I did when I first saw your image, and if one takes the view that the power in the jet is somewhere between 10 to the 43 and 10 to the 44 ergs per second, which is what you sort of typically need to inflate the Virgo cluster and so on, it's much greater than the bolometric power of the source. You're seeing a good fraction in millimeter. You're seeing a good fraction of the power that we know about coming from around the black hole and then say an accretion disk and so on. And it's 100,000 times, maybe even probably at least 100 times greater than the power of the source. So now it could be we're in a low state now, so the jet power is really rather low. I think that's probably a serious idea. But if you just take this naively, then the magnetic fields we're talking about, and again, elaborate models have been made with a much more intricate answer to this, but it's typically in the 100 to 1,000 Gauss range, and that to me implies an enormous magnetic stress, enormous magnetic pressure, and correspondingly a cooling time for the emitting electrons at millimeter wavelengths. There's maybe minutes or as small as that. I mean, it could be somewhat longer, obviously, but it's still a very short cooling time. And if you make the most naive estimate of the gas pressure, which would be something like the millimeter power times the cooling time divided by the volume of the torus, that's the sort of a natural sort of cooling time, that's much, much less than the magnetic pressure. So my inference, which was different from the one that was in the 60,000 simulations, was that this was actually, the whole thing that you were looking at was essentially a magnetically dominated region. The whole thing is a magnetically dominated region. I'll come into that in a moment. And at least I'd still take that sufficiently seriously to think more about it, even though it's clear that the weight of publication opinion is very much in favor of an alternative view that you've got an accreting flow in a torus. So this is a cartoon that I'll refer to several times, and I'm going to, as I say, in placing this alternative on the table, I'm going to contrast the left-hand side of the background of this diagram with the right-hand side. The left-hand side is just a cartoon, and it basically says that you have a very hot torus there, just shown schematically in orange, and it's got relatively cool, it's supported by the pressure of hot ions and relatively cool electrons, and they have to be kept cold. It'll deflate if it radiates too much. So those electrons have to be kept relatively cold, and that may be quite achievable. It's not a very propitious argument for preventing ion electron heating, as many of us worried about a long time ago. But it is certainly possible, and then that can, in some sense, define in a very most simplistic way that's borne out by observations like the many ones I could show there, including the ones you all made. But here's one. Bottom left-hand corner, I think it's from Repaired et al., and of the flow in this sort of region. And the alternative view is that what you're actually looking at in this sort of ring around the black hole, which will be rotating and Doppler boosted in the approved way, is essentially a magnetically dominated region, and you're looking at current sheets in that magnetically dominated region. And I'll just outline the general alternative conception of what is going on. Instead of having gas flowing continuously inward in a more or less conservative way onto the central black hole in sources like M87, different story for the quasars and so on, but in sources like this, having gas flow conservatively onto the black hole, instead what you have is the spin of the black hole not just powering the jet, in this way here, with the magnetic field lines threading the horizon of the black hole, but also sending enough electromagnetic power transversely across this magnetic surface here. And there's a flux of angular momentum primarily is what's important, but also energy outwards, and it's enough to essentially drive away all the gas, and the gas that is being driven away, I call another Latin construct called not an accretion disk but an ejection disk. So you've got gas, a large amount of gas that comes in at large radius, and it's all driven away in a hydromagnetic wind. And this hydromagnetic wind can collimate and illuminate the jet. Sorry, oh wait a minute, that way. Yes, can collimate and illuminate the jet. Now, I'm going to come back. There's a rather subtle point here, which I'm going to come to. If we start thinking about this region around here, which is called the ergosphere, or I now call it the ergomagnetosphere, if you call this region around here like this, then it's a region where kinematically observer on a time-like geodesic is going to have to rotate with respect to infinity, and the minimum angular velocity is positive. And it's also the region in which negative energy orbits exist. And so the Penrose process can exist in the way that Roger first conceived it. And so this is a sort of a simulation for, I think it's from Parfrey et al. And here's a more recent simulation. And there's two conceptions of what might be happening in these circumstances. One is that there's a current sheet here, and essentially these magnetic field lines all go into the horizon like that. And the alternative view is the field lines actually go through the equator like this, and I'll explain what the implications of that are in a moment. And those field lines essentially go through the equator. They don't form a current sheet in this way, but in fact the field lines just go through the equator, whoops, like that. And this is, you know, in some sense, that's the region that you're looking at. So if I say a little bit more about this, and I'd like to just say something that is well known by those of us who work in this business, to distinguish MHD from force-free models. If we take relativistic MHD, we're making a continuum approximation, we're giving a fluid velocity, a magnetic field, a density of some sort, a pressure, an equation of state, and all of that, and we're not asking any detailed questions. Alternatively, we can take another extreme view, is to take the force-free view, which is also in some sense continuum mechanics. It's the way Maxwell actually did his electromagnetism. You know, Lorentz forces and so on didn't come till 30 years later. He knew about particles, of course, but didn't put it in his book. So here it's just pure continuum mechanics with charge density and electric field and currents and so on. And there's no reference to the microphysics, and there's a presumption that the microphysics adapts to the continuum mechanics in much the same way that oceanographers know that water is made of molecules, but they don't care about it very much. They know there's maybe some viscosity there, but when they're trying to understand a tsunami, they're not worried about molecules. It's not, you know, from the ground up, it really is continuum mechanics, and whatever lies beneath sort of adapts to it. So that's the sort of extreme view, and I think it's an interesting one and an important one to follow. And it's a, you know, completely causal theory. Now, if you are a sort of reductionist and you say it's the plasma physics that drives what we observe, then you'll, you know, there's been tremendous progress, sorry, in all of these things, but in the particle and cell codes at the, whoops, that seems to be rather unstable. And these, you know, I showed the Parfrey et al. And the other by Philipov and his collaborators. These, you know, all of these techniques have shown tremendous advances in simulation and so on. And they're looking at things at the kinetic level, and they have to have obviously artificially large Larmor radii, because the ones around M87 are probably centimeters in size for the particles you care about. But still, you learn a huge amount from doing these simulation investigations. And you know, as a sort of participant in some and an observer in many more, I'm sort of thrilled by the ability that people have of being able to develop and do these codes to teach us a lot. But there's still a long way to go to make the hybrid codes that essentially take the kinetic level investigations and combine them with some sort of continuum mechanics like this. So this is sort of perhaps too long. I probably should not say, I'm going to be running out of time, so I'm not going to say too much about this. This is in some sense the way of getting spin energy out of the black hole, is to have field lines that cross the horizon, and basically it looks like you're doing something that's forbidden, but you're not. if you were an observer sitting above the horizon in the ergosphere, traveling with, as you must, in a positive angular velocity, then you would see energy going into the horizon. But if you're working in the frame at infinity, where energy is the conserved quantity, then energy comes out of the horizon, and it's all just a transformation with angular momentum and so on that makes this happen. We can think about this not in terms of fields, but think about it in terms of currents. Then we'll have typically in a powerful quasar, say 10 to the 18 amps and 10 to the 20 volts, and that'll give us 10 to the 45 ergs per second of associated with the electrical circuit. And what a radio astronomer is looking at is the dissipative load of this. And there's an internal resistance to the battery, which is the increase in mass that will go alongside this. So that's a sort of, there's much more that can be said about this, and then maybe in some of the later discussion I'll come back to this. But let me just say here, and what I think the sort of ergomagnetosphere problem is, and this is, and I think there's a possible solution to it. One is, if we imagine some field line that threads the ergomagnetosphere, but not the black hole shown here in green like that. That's a magnetic field line. Then, as I said, if you just think about it like an observer, and you can make this formula, of course, but it will move. It'll have to move with a positive angular velocity. It can't be at rest, and that therefore means that if there are conserved quantities along this field line, then if there are conserved quantities along that field line, then it's going to take away energy and angular momentum. It can't take it directly out of the hole. Where does that energy and angular momentum that's carried away here, where does it come from? And I would say that what in practice happens, and this is a sort of much longer and more interesting story, what in practice happens is that this field line gets dragged back to the minimum angular velocity it can have, which is still positive in the ergosphere. And at that point, what you're effectively looking at is that the Lorentz invariant E squared minus B squared becomes positive. So it becomes an electric zone, an electric region. And as I think may also be the case in fast radio bursts and so on, that leads almost generically to instabilities under force-free rules, not thinking about this kinetically, just thinking about it as just continuum force-free mechanics. That leads to instabilities on all scales, and that will essentially radiate backwards lots of force-free type electromagnetic waves backwards, which will be something to push against and will give you the energy and angular momentum that you need to carry it away in the wind. So that's the story, and it's a very different view from either the kinetic simulations of Parfrey et al. Or the many wonderful MHD, relativistic MHD simulations associated with EHT and many others. So this is a summary of what I just said here. And so if I go back to my original slide, then just to emphasize the story a little bit more, these field lines that thread the ergomagnetosphere, then there's this zone which separates the ergomagnetosphere, which is the rays of 2m, from this ejection disk, and I'll call this a clutch. This is a clutch. And in simple force-free axisymmetric analyses, energy and angular momentum only travels along the field lines. But if you think about this for a moment, I would make the conjecture, and it's backed up a little bit more, and this is work with Naomi Globus and others, that the energy and angular momentum cross these flux surfaces, surfaces in the same sort of spirit that they do in the nonlinear development of the magnetorotational instability in the conventional accretion disk. So there's a flux of energy and angular momentum outwards, and there's plenty of energy and plenty of angular momentum here to blow away all the gas in the disk, and the gravitational binding energy released by the accretion is nothing compared with the power that's coming out of the black hole in all places. So that's the sort of story. I've done that. Avery, by my clock, I must be nearing the end of this talk. Is that correct?
I think if you have one more slide, that would be great.
Well, what I'm going to do is show about 4 or 5 slides by title. and they can come up later, and then I will give a summary, okay?
Sounds good.
Okay. Firstly, I've been particularly fixated about the gamma rays, how they made, and the larger picture of the jets, particularly in 3C279 and sources like that. There's a story there. It's a rather different story from the conventional one. It involves the beta-Heitler process and using relativistic protons. There's a similar story, a similar issue about how does this relate in the case of quasars, not so much M87, but the quasars, where did the broad emission line comes from. And here the story is that what you're looking at is that the gas that you're looking at in the broad emission lines is flung out in these hydromagnetic winds from a much denser disk. Sorry, that's a mistake. Then there's the business of acceleration. Shocks are great, but most of us think that in this environment, they're probably not the dominant accelerator, in situ accelerator, and non-relativistic reconnection is famously not terribly good accelerator, but relativistic reconnection is different. There have been wonderful simulations. It's just one of many, and this is natural thing to happen in a shear boundary layer. And so it's hard to believe that this isn't terribly important. But I'd like to put on the table an alternative, which I call magnetoluminescence, which is if we cartoonly think about magnetic field lines as twisted flux tubes, and they can make little slip knots, and they can make non-topological changes that can release a lot of magnetic energy, as shown in this cartoon here and not in this trefoil here. And this untangling can also release a lot of energy along with the reconnection, which is a somewhat slower process which you would see, for example, at that point there in the trefoil. Moving on, in the larger context, there's of course much more coming in. Some of this is going to be discussed in this meeting, but some of it is missing. The X-ray reverberation is very exciting. They're measuring spin, seeing behind the horizon and so on, and arguably also trying to validate GR. There's the binary black holes, which will be discussed, I think. Exciting prospects from pulsar timing arrays and so on, marginal detection of the gravitational wave background, perhaps. Interested in hearing a lot about that. There's things about AGN taxonomy, environmental impact. Black holes are terribly important for cosmologists nowadays, and after a decade of ignoring them completely, they now ascribe magical powers to them, and it's wonderful. And then ngEHT, it's hubristic of me to make any comments, but that won't stop me. Clearly, you've got these great opportunities, and I'm eager to hear what progress you've made. Greenland and perhaps east-west baselines going to Africa, perhaps, and Asia are very exciting prospects. And then there's dangling out there is the prospect of space, where the challenge is to ask, do you go small with a few small dishes in low Earth orbit coupled to ARMA, or do you invest all your resources in a very long-term, very ambitious project with longer baselines at L2 and all of that? I don't know what the right answer is, but it's the debate that ought to be happening with further now. And if I just finish with the summary slide, as I promised, let us all celebrate the tremendous accomplishments at all levels by EHT. It's technical, scientific, political, international, and public outreach. You really have, Franz Cordova told me that cat's eye was the most downloaded image from the NSF. That's telling you something. And this, of course, I think we wouldn't be here otherwise. We think this is the beginning, not the end of the story. Black holes exist, but then for me, it's always been the question is, how do they work? Are they just an empty stage, or is there a lot of new physics, theatrical scenery? Are there properties, their intrinsic nature, or consequence of their histories? Now and then, is the behavior of a black hole just what it is today, or is it a consequence of accretion flows from very much larger radius? Is the gas in an object like M87 ejected or accreted? I've argued for ejection for a long time, but it's decidable observationally. Is it magnetic field or gas that's really confining everything close to the black hole? Are we looking at a volume or a surface, and so on? And then, this, where you go, in terms of planning, which you're going to spend a lot of time talking about, you go for an incremental or a transformative program. And, you know, I'm very excited about the prospect of building up these hybrid simulations and building on all the wonderful accomplishments that have been made by simulators in putting together a set of stories about the black holes. And I'm hoping that they'll look at a larger set of stories and decide which of them is the truth. So thank you very much indeed. Sorry for going on slightly long, but I wish you well in a very exciting meeting, and I'm certainly going to be listening to it as long as other commitments allow me to do so.
Thank you, Roger. So again, in lieu of having a live audience, let me offer applause for everybody. Since we are now 5 minutes into the first coffee break, and I imagine everybody wants to refresh their cup and take care of any other immediate responsibilities, let's curtail questions now and hold them at the discussion session at the end of the morning talks. Look, can I just note two things that leapt out at me? So the first is clearly there are many astrophysical mysteries still to answer, and so that's going to be you know, quite an interesting story over this week, trying to lay out what those are and how we might address them. And second, to all of the graduate students out there listening, 2 decades after your thesis is submitted, you may still hear it referenced in your advisor's talks. So do take care to make sure that you're happy about that. So thank you, Roger.
Thank you, Avery. What time is this question session, if I might ask?
It's just before